everyone. In preparation for some problems that we're going to do in class, I thought I would show you a complete example of how to do a confidence interval for a proportion based on a word problem, which is pretty indicative of what you're going to see in most of Chapter 8. So remember that a confidence interval is a way of estimating a true unknown parameter. And that parameter can be different in any problem. And the first step is to identify what is that thing we're trying to estimate. And with what we know about the normal distribution and how sample proportions behave in repeated sampling when we have a large enough sample size, we can use the predictable percentages in the normal model to find a reasonable range that should contain the true whatever it is we're trying to estimate. And we've been focusing on estimating proportions. So this problem is about alcohol abuse, and it's defined as binge drinking is more than 5 drinks in a row 3 or more times in the past 2 weeks. So if I read through the problem and identify kind of the key pieces, I see that a survey of 10,904 randomly selected, that's good. U.S. college students collected the information on drinking. And what was found is that of that group, 2,486 were defined as binge drinkers. So when I read a problem, the first thing I usually want to do is identify, well, what do I know? All right, I know that the sample size is 10,904. And then we could call this X, right? The number of successes out of the sample. And then with that, we would be able to calculate the sample proportion. So if we complete that piece, we find that the sample proportion of binge drinkers in this sample is 0.23 or 23%. So that's the number we're going to work with to try to create our confidence interval. That's our best estimate for the true parameter. So part 1 asks us to identify the parameter of interest, the thing we're trying to estimate, and we want to be pretty specific with this, so I'll just write it out. We'd identify the parameter of interest as the true proportion of U.S. college students classified as binge drinkers. Now, before we do a confidence interval, we have to take some really important steps, and those are checking certain conditions that actually allow us to do 2 things. We need to be able to calculate the standard deviation of the sample proportion, and that relies on independence. And then we need to be able to use normal calculations. So we have to be sure that the sample proportion would have that normal shape. So when checking independence, we have to think of just a couple of things. So there are kind of 2 ways the observations can be classified as independent. One, we have to check to make sure the students were selected randomly from the population of interest. And we also are going to have to check the 10% condition. So here's how we would check for independence. The students were selected randomly from the population of interest, and we can assume that the sample of 10,904 is less than 10% of all college students. That is a reasonable assumption because some colleges are, some colleges alone are 3 or 4 times this sample size, really large colleges, big universities. So we're not removing too big of a portion out of the population. So basically when we check this condition, we're making sure that removing the sample doesn't change the composition of the population that remains. It's all pretty much the same. And say removing students who are binge drinkers isn't going to change the percentage of binge drinkers who still remain in the population all that much. And then we have to check for normality. So we could say we're checking normality here. And this is where we have to check the large counts condition. So basically, we have assumptions and conditions. We're assuming independence, we're assuming normality, and then the conditions that we check are ways to allow us to make those assumptions. That's kind of a subtle distinction that's a little bit important. So we've got to check large counts. So we're going to check n. We used to check np greater than or equal to 10 and n times 1 minus p greater than or equal to 10. But remember, we don't have the true proportion anymore. That was chapter 7. It's a whole new world now, whole new ball game. So, and this is going to work out. It's pretty obvious because we have 10,904, and the sample proportion that we calculated was 0.23. So basically, we're just counting the number of successes and the number of, we could call these failures. Not that we say binge drinking is a success, but as it's defined in probability, it is. So then we have 10,904 times 1 minus 0.23. Okay, so these should work out to 2,486. And we are in great shape here. I mean, it seems like maybe overkill that we have to check this condition, but it is super important. Can lose a whole point on a free response problem without checking conditions correctly. So we would summarize and say, we can assume and this part's really important. We want to identify what is the random variable here. It's the sample proportion. We can assume that the sample proportion will follow a normal distribution if we were to take many repeated samples of the same size from this population. And that's critical because that part in the confidence interval where we add or subtract 2 standard deviations or however many standard deviations, we need to be sure that that is a reasonable thing to do, that this sample proportion actually does follow a normal model. So we've checked our conditions, we're all good to go, we've identified the parameter, and now we can actually do the calculation. So first we're asked to find the critical value for 99% confidence interval. And we had practiced this in class, and it all goes back to this idea that the sample proportion is normal because the sample size is large enough. So 99% falls in the middle, 0.99. And then we figured out that kind of the best way to do this is to pick the lower tail and say, let's get the critical value, and we call that Z star. So let's just put a little Z star here. So when we see critical value, we'll know what we mean. Critical value is how many of those standard deviations we're going to add and subtract in order to create our estimation interval. So if we take out the middle 99%, we're left with 0.5% on either side, or 0.005. So here's where then I need to use the table or my calculator to figure out what is that thing. So Z star is absolute value of inverse norm. And that's absolute value just because we already have a positive and a negative as part of the calculation of the interval. So let's go ahead and do this on our calculator. So we do second vars, inverse norm, 0.005 0 and 1, those are mean and standard deviation of standard normal. We can leave it. 2.576, you'll start to memorize that number. Okay, so I'll write it out. So inverse norm, so 2.576. So that goes into our interval. So let's write out the formula for the interval. And it's usually plus or minus, but I'll do minus separate and then the plus on the other side. So it's this times critical value times the standard deviation estimated. Now it's actually, I shouldn't say it's the standard deviation. We now call it the standard error because it's an estimate. So just think E for error, E for estimate. That'll work. All right, so then we can plug in because now we know everything. So we're going to go ahead and say 0.23 was our estimate, 2.576 was our critical value. And we can already see we're going to get a very small standard deviation, very small standard error. Okay, so I worked out the margin of error. So the formula now looks like this. I found that this whole, the 2.576 times the square root of 0.23 times 1 minus 0.23 all over 10,904, that worked out to be just about 0.01 if I round. And then on the other side, everything looks the same except I'm going to be adding that that margin of error. So here's a little cheating way. Okay. So then over here I'll have 0.23 for my upper boundary, 0.23 plus 0.01. So my interval just works out to be then 0.22 up to 0.24. Very small interval, right? Why is the interval so small? We can see right from our calculation that dividing by this huge sample size greatly decreases the sampling variability. So if we were to take repeated samples of over 10,000, those sample proportions are going to be very close to the true proportion on average. So we don't expect a lot of deviation. So this is our estimation interval for the true proportion of binge drinkers. And again, it's important for us to interpret correctly. Something like that. We're 99% confident that the true proportion of college students who binge drink is between 22 and 24%. So why might this be useful? Well, Department of Public Health might be interested in figuring out how big of a problem is this, what kind of interventions are necessary. So confidence intervals are used often to figure out things like that. How big of a problem is this? What is the magnitude of this phenomenon that we're observing? Okay, so that's confidence intervals. After watching this, you should be able to do another problem like this, and then we will add a few elements to this topic of confidence intervals. There are some really pretty tricky kinds of questions that we see, especially in the multiple choice question. So make sure you're solid on this for class so that we can kind of take it a little bit further.